Watch this. 8 blades, perfectly spaced around a circle. I move one slider, 16 blades. I move it again, 24. Every single time, Grasshopper divides the circle equally, instantly, with zero manual rotating. This is a polar array, one of the most useful techniques in all of parametric design. And today, day 15, we are building it from scratch. This is also the start of something bigger. Days 1 through 14 were about getting comfortable with Grasshopper's logic, sliders, data, basic geometry. Starting today, phase 3, we move into parametric geometry, the techniques that actually starts looking like real architecture. Polar arrays, linear arrays, attractors, subdivision. This is where the series gets fun. Let's get into it. Before we build anything, I want you to see where we are headed. This is the finished file for today, a count slider driving a fully radial pattern. Watch what happens as I drag it. Every copy stays perfectly spaced, no matter how many they are. That's the entire lesson in one clip. Now let's build it from an empty canvas. Every polar array comes down to one formula, and once you understand it, the grasshopper part is easy. A full circle is 360 degrees. If I want n equally spaced copies, the angle between each one is 360 divided by n. 8 copies, 45 degrees apart. 12 copies, 30 degrees apart. So, copy number 0 sits at 0 degrees. Copy number 1 sits at 1 times that angle. Copy number 2 sits at 2 times that angle. In general, the angle for copy I is I times 360 divided by n. That's the whole formula. Angle equals index times 360 over n. Everything we built today is just this formula translated into Grasshopper components. Keep this formula in your head for the rest of this video. Angle equals index times 360 over n. Every component we add from here is just one piece of this equation. If a step ever feels confusing, come back to this formula, it's a whole lesson. Let's build the index list first. That's our I from the formula. In Grasshopper, the component that generates a list of increasing numbers is called series, and it lives under the sets tab. First, the index list, our I. Series gives us exactly that. Start at 0, step by 1 and generate as many numbers as our count slider says. Right now that's 0 through 7, 8 index values for 8 copies. Now, we turn those indices into actual angles. That's the expression component's job. Every expression component ships with two inputs already named x and y. I'll wire our index list straight into x, no renaming needed. For the second input, I rename y to n, so the formula reads clearly and connect the same count slider into it. Now the formula x times open parenthesis 360 divided by n close parenthesis. That's our polar array formula, typed exactly as Grasshopper expects it. Check the panel, 8 angles, evenly spaced, 45 degrees apart, exactly what we calculated by hand a minute ago. Quick but important step. Grasshopper's rotate component doesn't think in degrees. Internally, it works in radians. If we plug our degree value straight into rotate, the rotation will be widely wrong. That fixes one component. One more component and this step is done. It's simply called radians, not degrees to radians, just radians. And you'll find it on the math tab in the trig panel. Feed our degree list into it and it converts every value in the list at once, all 8 numbers through a single wire. Compare the panels. 45 degrees becomes about 0.785 radians. Same angle, different unit, and now it's a unit rotate actually understands. Here's a detail that trips up a lot of people the first time they try this. If you rotate a shape that's sitting exactly on the rotation center, all your copies just stack on top of each other. You won't see a fan at all. The shape has to start off center, reaching outward. Let's build one blade. We are building one blade and we are building it deliberately off center. The X domain runs from our insert value, a small 0.3 unit gap out to our length slider. That gap matters. It's what keeps the blade from overlapping at the middle once we array them. The Y domain is centered on 0, running from negative half the width to positive half the width, so the blade is symmetric around the x-axis. Feed both domains into a rectangle component, leave its plane on a default world xy and you got one rectangle sitting away from the origin reaching outward, exactly the shape of polar array needs. This is the moment everything connects. One rotate component, one rectangle, one list of angles. And what comes out is not one rotated rectangle, it's 8. Let me show you exactly why that happens because understanding this is worth more than memorizing the steps. Look at the inputs on this rotate component. G has 1 rectangle, A has 8 angles, P has 1 plane. 3 inputs, 3 different list lengths, 1, 8 and 1. So why do we get 8 rectangles out, not 1 or an error? This is Grasshopper's data matching, and it's one of the most important ideas in this entire program. Whenever a component gets list of different lengths, Grasshopper doesn't stop. It stretches the shortest list to match the longest one, repeating their only value as many times as needed. Our rectangle and our plane each have exactly one item. So Grasshopper quietly repeats that one rectangle and that one plane 8 times each, once for every angle in our list. Rotate, then pass them up. Angle 0 with copy 1, angle 1 with copy 2 and so on, all the way through the list. One component, one calculation pass, 8 fully formatted, correctly placed copies. No loops, no copy pasting, no manual rotating. This is why parametric software is fast. Let's turn this into something you actually use on a project, a parametric column capital. The decorative head of a column built from radial fins around a shaft. Same technique dressed up architecturally. Everything from the last minutes, it's still doing the work here. Series, expression, radians, rotate. All we are adding is context. A circle standing in for the column shaft and our extrude component to lift our flat fins into standing 3D blades. Extrude just needs a base curve, our rectangle and a direction, a vertical vector scaled by the height slider. Now, instead of flat blades on the table, we got a genuine radial capital. 20 fins evenly spaced standing around a half unit shaft. Change count, length, width or height and the whole capital redesigns itself instantly. Here's today's challenge, and it's great one. Instead of every blade being the same size, what if the size itself change as you go around the circle? Big in the middle, small at the ends like the flower opening. One more expression component gets us there. Same trick, new job. This expression uses the same index list and the same count value, but instead of producing an angle, it produces a scale factor using a sine curve. The key detail is that little minus 1, n minus 1, not just n in a denominator. That's what makes index 0 and the very last index both land back at a scale of exactly 1, so the pattern closes the loop cleanly instead of leaving a visible seam where it wraps around. Feed that scale list into a scale component alongside our rotated geometry and every single copy gets individually resized all in one pass, no manual scaling required. You build a working radial fan, a parametric column capital, and a blooming flower variation, all from one count slider. Tomorrow, day 16, we stay in phase 3 and tackle linear layers, the straight line cousin of what we did today. Perfectly for window mullions, facade panels, and repeating structural base. If today clicked for you, tomorrow will feel very familiar. If this helped, hit subscribe so you don't miss day 16 and drop a comment with that what you're planning to build with your first polar arrays. See you tomorrow.